Hey there ladies and gents, I'm now printing the rotor, which is the final part I will need to construct the C.M.G. It's been an on and off project now for the past couple of years. In the past few months, got back into it again. I now have a new 3D printer, the Artillery X1. After a bit of tweaking and fault finding, it's turning out to be a really good machine. I'm using Cura as the Cura is a slicing program to produce the parts themselves. So they're nice and shiny, as you can see. Dimensional accuracy is okay. I'm sort of having to put it to 0.2 give or take on each part to slot together properly. So this is the base plate itself. It's got 40% infill, 3 walls, 3 top and bottom. Layer thickness again very rigid, like quite nice sturdy part in itself. So we've got the tabs there for the outer core, which are these 4 on the outsides, and then the 4 on the inside are for the inner core with the support for the arms themselves. And they get this little sort of ditch here is just to give any clearance to the magnets in the rotor, maybe not seating down properly or any slight wobble, give or take. Might as well engineer it in just to engineer it out. So this part here, now the parts within the circle of magnets, that is the inner core itself. This retainer ring on the outside is an experimental design part for constructing constructing the magnets themselves. So once these are all actually stuck in place, they will be one half repelling, one half attracting, as it was, or one north, one south, all of it pretty much repelling from each other except for the two at the, which will be center points. So from this point here, sort of north and south, that's all one field, and then that side will all be one field. I'm using ceramic bearings to reduce any friction. I have used metal ones in the past, double row, single row, 2 single rows and split sort of orientation like this one. But ceramic bearings are really good, like really low friction, and I think going to be important as part of this design again, maximising the energy gained from the concept of how it's supposed to work. So this ring here doesn't need to be here. I'm just missing a magnet because I broke one. If I remove this, it will destroy the rest of these. So that's there in that place. Just to show actually, the tabs on the inside here will slot to the tabs on the inside there. It takes a bit of force to push them into place because of the tolerances. It took me a lot of force to get them apart just to do this video. And then the final part is the outer core itself, or the outer rotor. Outer core? Yeah, outer core. 40 magnets, that's going to be 30. So that's 30, that's 42 magnets, 72 total. And again, it will be set up as orientations, one side north, one side south. So this has been re-engineered, reprinted, to try and compensate for the PLA shrinkage, both when printing, obviously across all of these, when printing, but also in environmental. So afterwards, the print was prone whilst handling it and constructing the part to expanding. PLA is thermal reactive, so the colder it is, there's more shrink. Room temperature, holding it hand, or environmental, it will expand, which was the main long-term failures of these particular parts. So the glue that would stick them together would fail more commonly on the inner core because the magnets are on an outwards orientation, so they've got somewhere to go. With the outer core, because they're on an inner orientation like a bridge, the parts lock each other in place as they are now until I start constructing it and actually putting the magnets in the repelling phase. That's where it can become very tedious and you could still have failures. So the main parts I've had to engineer out of these, again, is the thermal related issues, in which I might have a sleeve on, well, I'm going to have a sleeve printed to go on the outer parts of these magnets to hold it all in. I had one before, it worked really well, but eventually biodegraded and failed, so I'm going to have a lip to stick to the inner core as well, just to help. with that for initial prototyping and testing. So with the outer core, obviously the main part of this is it all needs to be round. In most cases, by eyeball, it seems round, which has been the biggest issue of this design for years. Having the magnets orientated flat, spaced correctly, has been one of the biggest issues to have. Now, to find out if it is correctly spaced, if it is a circle, or if there's any wobbles or issue points, I have to do a full construction. I can't do sort of a half, oh yeah, that's okay, tweak it, do the thing. That's the drawback of this design. I will have to build it as fully, ready to go model as it was prototype. Again, this is complete prototype. And then find out that it does, or in most cases didn't work, because I've found sticking points. Now they occur because the magnets are set up like this, where you got your pinch point and the expansion point, which is at the top. This expanding point needs to do that. Now, if the magnets are stuck and it's a fraction of a mil out, which most commonly it was, or it wasn't flat against the face, it was slightly twisted or rocked or anything like this, that difference that I need from here to here to make the magnet move out of that position can be stopped. Initially it will fly through it because it will gather its momentum and it will work, but if I do it slowly to find all these little imperfections, which is what I would like to engineer out, I find that yes, there's sticking points along the route, which is a loss of energy. Simple as that. Obviously I don't want that. I want to get as much as I can, full rotation, nice and solid and continuous as well, hence the name continuous magnetic gate. This is the biggest problem I'm having to work with, but obviously with the use of a 3D printer, a bit of CAD software, a bit of time and effort, maybe some sandpaper too, I will obviously build it and see if it works. I do have on the table behind me another one of these rings with complete magnets, fully constructed, different brands of magnets. This is one of the other things that I've been having to deal with, is manufacturers themselves, they say, oh yeah, it's XYZ magnet, this is the dimensions, fantastic, you get the part. So it's not the dimensions. Whatever method of manufacturing they, let's say, produce the neodymium magnets to the actual size of the magnet, and then add the chrome plating on the outside, which expands the dimensions, or are the ones where they compensate for that and produce a smaller size to the right size. But I can't mix and match the magnets again because I've got so many. To have different types, I'd have to re-engineer the whole thing to compensate for difference in magnet sizes, which is stuff that I just don't want to have within this design. So sticking to one supplier helps a lot. So this is the rotor. As said, it's printed away, nearly done for the surface, 20mm per second, just to make sure it actually sticks to the build plate, which is really good. Excuse me. It's a really good glass build plate, so when it cools it just pops straight off. Great help for parts like this, where it's a large amount obviously stuck onto the build surface. Prying it off with pliers and stuff like that, no good, or scraper or anything like that, forget it. If you've got a detachable build plate, that's good, but make sure the part is fully cooled before bending and flexing the part itself. I don't know if you see it on a few videos before where people print something, it's done, they immediately get it off the machine and then start ripping it off the build plate. How good for them, that's fine, but by the way, your part's still warm and it will flex and bend. So having a glass build plate prevents me from doing that out of just sheer let's get on with it, bit of patience. It will cool and pop off in its own time and hold its dimensions. And sometimes when it'd be like off the build surface, I can move it and it's like it's still vacuumed, even though it slides around, it's still vacuum stuck to the build surface. So that's actually a really good indicator of how just flat and solid it is. So these are the parts itself. 2 months or so. Been re-engineering it due to a misalignment within SketchUp. That's the program I'm using. Yes, I do have Fusion 360. However, I just can't use it. I just can't seem to produce a part. I guess I've got stuck into a different build process, and SketchUp, because it's so janky sometimes, and actually mix matched, or I can build just from junk. I don't always know the accurate dimensions. I don't always know the part sizes. I have to reverse engineer it from the results of the previous one, and then factoring in, factoring in tolerances and misalignments of the machine itself. So yeah, ceramic bearings there, £15 each, 30 magnets. So I think that was about £20 itself. You're looking about £20 of magnets there. That's about another 30 quid. So, and then PLA and the 3D printer itself. So nothing comes free, of course, until maybe. Oh, I can only live in hope. So that's how things are for the time being. Again, this is a project I'm doing on myself because there's an idea I had, and I'll just see how it goes. That's why I don't want to release too much information about it or all the little development ideas, because there's bloody hundreds of them. I've done videos over the past couple of years, working with the tolerances of each machine, or issues within design and material properties, basically. But I don't really want to keep putting them up onto YouTube or all that stuff, because if it turns out to be nothing, which possible, I'm open to that. That's cool. At least I learned something. At least I had to go myself. And I'd rather be, hey guys, yeah, this is how the project went. Couldn't get it to work. If I do achieve that it's dimensionally accurate and there's no sticking points and everything that I could have done to it, then it's like, yeah, well, that's the idea. This is how it goes. As a project, try another idea. This particular one I couldn't get to work or didn't work, so I don't want people wasting money, time and effort on trying to do this stuff, as I've seen with many other designs out there. It's all good and well, but in the long run it doesn't get anywhere. So I'd rather have it this way, that I spend all the time and effort and money on messing around with this, and do that. Yeah, if it does work, or at least if my version of it works, I'll say that if my version does work, well, this is 3D printable STLs, put it up onto something like Thingiverse. Hey guys, I've achieved Overunity, at least my device has. This is how it's working. STLs available for 3D printing. Can you reproduce it? Can you verify it? And go from there. Rather do it that way round than uploading hundreds of videos of nearly there, not quite there, or this, all that. So this is where the project sits at the minute. That's where the dog sits. And yeah, it's going to be just nearly done now. And yeah, the great thing about the Artillery X1, it is a quiet machine. It's not the quietest, of course, but it is a quiet machine. It went through a phase of being unusually loud. I wouldn't say as loud as my previous machines, but unusually loud for what it was, and it turned out more or less to do with the speed and acceleration resonating in the machine itself, or something wrong with Slicer, the program Slicer. After switching to Cura and tightening up a few things as well, it's got a lot quieter and a lot more stable. Yeah, I'm filming on my phone, so it's not exactly the best, but it does pretty much show that the layers are really good, nice and clean. Okay then, well, that's where things are at this point. Thanks for watching. You guys take care, and I'll see you later.